before humans ever opened their eyes to the sky, the universe had already lived through ages of darkness, fire, collapse, and silent creation. Before Earth, before the sun, before the first cell, something vast and deeply unsettling already existed. Scientists have traced that past backward through stars, atoms, radiation, and the birth of time itself, and what they found is far stranger than any lost world or forgotten civilization. In this video, the journey goes deeper than history, deeper than life, into the terrifying truth of what existed before humans. If this is the kind of cosmic mystery worth exploring, like the video, subscribe to the channel, and stay for the full descent into the oldest reality science can reach. At the farthest reach of present observation, the universe appears not as a wall or a border, but as a limit set by time, light, and expansion. Scientists call this reachable realm the observable universe. It is not the whole universe in any confirmed sense. It is the portion from which light, or some other signal that obeys the same speed limit, has had enough time to arrive since the early universe became transparent. Beyond that reach, space may continue for an immense distance. It may even continue without end. Observations do not yet decide the full extent. They show only that human knowledge begins inside a horizon made not of stone or gas, but of causality. This is the outermost region that science can map in practice, and it is already vast beyond ordinary language. In every direction, telescopes gather light that has crossed deep time. The farther a galaxy lies, the longer its light has travelled. Looking outward becomes a way of looking backward. A nearby star in the Milky Way appears in something close to the present, though even that light is old by the time it enters an eye or detector. A distant galaxy appears as it was millions or billions of years ago, at the greatest distances now observed. Some galaxies are seen in youth, their light leaving them when the universe is still young. Distance and time fold together in this way, so the edge of observation is also the oldest visible record of cosmic history that matter can present in direct form. Yet that visible edge is not simple. Space itself expands. This expansion means that galaxies are not merely moving through a fixed emptiness like sparks through still air. The emptiness between large structures changes with time, over immense distances. This stretching of space shifts light toward longer wavelengths, a change known as redshift. Redshift is a lengthening of light waves. It is one of the main signs that the universe expands. The greater the redshift, in general, the farther the source and the earlier the time from which its light comes. In this outer region, science does not find stillness. It finds a universe whose scale changes while observation is taking place. A universe in which the act of seeing the farthest things is inseparable from the history of expansion. The size of the observable universe is often misunderstood because its age and its radius are not the same number. The universe has existed for about 13.8 billion years according to current measurements, but the most distant matter now observable is much farther away than 13.8 billion light years. This is because space has expanded while light travels. The present radius of the observable universe is estimated at about 46 billion light years. This does not mean that light moves faster than allowed. It means that the fabric of space between distant regions has stretched over cosmic time. In this outermost frame, common intuition loses its grip. Straight lines remain, clocks remain, light remains. Yet the geometry of the whole behaves in ways shaped by general relativity. The modern description of gravity as the curvature of space and time. The observable universe is not centered on Earth in any special physical sense. Though it appears centered on any observer, every distant observer, if one imagines such a being in another galaxy, would also stand inside a sphere of observability defined by the time available for signals to travel. This symmetry matters. It removes old ideas of a privileged middle. The cosmos, on the larger scale studied, appears broadly uniform when averaged across great distances. This property is called homogeneity, when matter is spread similarly in different large regions, an isotropy when the universe looks much the same in all directions. Neither term means perfect sameness. Galaxies, clusters, and voids create local pattern, but on the grandest scale, the distribution smooths. The outer region therefore offers an important lesson. Before any living observer appears, before planets, oceans, or bones, the universe already follows rules that do not bend around human presence. Even so, this outer boundary carries uncertainty. Scientists can describe the observable universe with increasing precision, but they do not know whether all of reality extends far beyond it in the same way. Some models allow a universe much larger than the observable part. Some allow spatial curvature so slight that the whole is effectively immeasurable with present tools. Observations indicate that space is very close to flat on large scales, meaning that ordinary Euclidean geometry works well across cosmic averages, but a tiny overall curvature has not been ruled out with complete finality. It also remains uncertain whether the total universe is finite or infinite. The evidence shows what can be measured within the visible domain. Beyond that, caution replaces certainty. The great darkness between the farthest sources is not empty in the casual sense. Even where no galaxy is seen, space contains thin matter, radiation, and fields. It holds the record of earlier conditions. Some of the older signals arrive not as visible light, but as radiation stretched into microwave form by expansion. That older glow belongs to a deeper layer of the story and remains behind the range of ordinary starlight. In the outermost region, however, the first task is simpler. It is to understand that the universe presents itself as a layered depth of look-back time, with the farthest visible structures marking a frontier of evidence. This frontier is not terrifying in the manner of sudden danger, it is unsettling in a quieter way. It suggests that what humans call ancient history barely begins to touch the age of the cosmos, and that the known past of Earth occupies only a thin, recent film near the surface of a much older reality. Before humans, before life, before the sun, before the Milky Way reaches its present form, there is already this immense observable domain, governed by expansion, geometry, and light. It does not wait for witness. It does not arrange itself around memory. It simply endures in lawful change. The farthest region known to science is therefore not a place of mythic origins, but a measurable horizon. It is where observation meets its present limit, and where the human story falls away so completely that even galaxies appear as brief events inside a larger and older order. Within the vast boundary set by observation, matter does not lie scattered without pattern. On the largest scales that can be measured, galaxies gather into an intricate arrangement often described as a cosmic web. This web is not woven by threads in any literal sense. Yet the comparison helps to convey the shape. Long filaments stretch across immense distances, linking clusters of galaxies like strands that connect denser knots. Between these filaments lie enormous voids, regions where few galaxies reside. The pattern extends across hundreds of millions of light years, forming a structure that is both ordered and sparse, dense and empty at once. This arrangement arises from gravity acting over deep time. Gravity, the attraction between masses, pulls matter together. In the early universe, matter is distributed with small differences in density. These differences are not large at first, yet over time, regions with slightly more matter draw in additional material. The denser areas grow denser, while less dense areas become emptier. The process is slow on human scales, yet relentless across cosmic ages. Filaments emerge where matter streams along preferred paths shaped by these gravitational differences. Clusters form at the intersections of filaments, where matter accumulates most strongly. Each cluster can contain hundreds or even thousands of galaxies bound together by gravity. These galaxies are not evenly spaced within the cluster. They move under mutual attraction, sometimes passing close enough to distort one another through tidal forces. Gas within clusters becomes heated to very high temperatures, emitting radiation that telescopes can detect in wavelengths beyond visible light. This hot gas, combined with the galaxies themselves, reveals that clusters are among the largest gravitationally bound structures in the universe. Between these clusters, the filaments carry a thinner distribution of galaxies and gas. The filaments are long and relatively narrow compared to their length. They guide the motion of matter, acting as channels through which gas and galaxies flow toward denser regions. The voids, by contrast, contain far less matter. They are not completely empty, but their density is much lower than the cosmic average. Light passing through a void travels with fewer interactions, crossing vast distances with little interruption. The overall structure, when mapped, shows a network that appears similar in every direction when averaged over large scales. This supports the idea that the universe is homogeneous and isotropic on those scales, even though locally it contains strong contrast between dense clusters and sparse voids. The cosmic web is therefore both structured and statistically uniform, depending on the scale of observation. This dual nature is a key feature of the universe as understood through modern cosmology. The formation of this web depends not only on visible matter but also on a component that does not emit or absorb light in a detectable way. This unseen component, called dark matter, reveals its presence through gravitational effects. Galaxies within clusters move faster than expected if only visible matter were present. The additional gravity required to hold these systems together suggests a larger amount of mass than can be directly observed. Dark matter provides a framework within which ordinary matter gathers. It shapes the web by forming gravitational wells that guide the flow of gas and galaxies. Computer simulations based on known physical laws reproduce patterns that resemble the observed cosmic web. In these simulations, dark matter collapses into filaments and halos under gravity, while ordinary matter follows, cooling and forming stars and galaxies. The agreement between simulation and observation strengthens confidence in this model, though the exact nature of dark matter remains unknown. Observations indicate its gravitational influence clearly, yet its composition is still uncertain. Light traveling across this web carries information about the structures it encounters. When light passes near a massive cluster, its path bends slightly due to gravity. This effect, known as gravitational lensing, allows scientists to map the distribution of mass, including dark matter, by observing how background light is distorted. Through such methods, the invisible structure becomes partially visible, revealing the underlying framework of the web. The cosmic web extends throughout the observable universe, connecting regions across distances that are difficult to imagine. It is not static. Galaxies move within it. Clusters grow through mergers, and voids expand as matter flows outward toward denser regions. Over time, The contrast between dense and sparse areas increases. The web evolves, yet it retains its large-scale pattern, shaped by initial conditions and the ongoing influence of gravity. In this region, the universe shows a balance between simplicity and complexity. The laws governing motion and attraction are consistent and well described by current physics, yet the resulting structures are intricate, with patterns that span enormous scales. The web is not designed or directed by any external force. It arises naturally from the interaction of matter, energy, and the geometry of space. Before the formation of planets, before stars like the sun shine, this structure already exists in a developing form. It provides the setting within which galaxies grow and evolve. The presence of such a vast and organized pattern suggests that the universe, even in its early stages, follows processes that lead to large-scale coherence. Observations indicate that these processes operate over billions of years, shaping matter into the forms now seen through telescopes. Uncertainty remains in the details. The exact properties of dark matter, the influence of other components such as dark energy, and the precise initial conditions all affect the evolution of the web. Scientists continue to refine models and gather data to improve understanding. Despite these uncertainties, the existence of the cosmic web is well established. It stands as one of the most striking features of the universe on the largest scales accessible to observation. This region, filled with filaments, clusters, and voids, represents a step inward from the boundary of observation. It reveals how matter organizes itself across immense distances. It shows that the universe is not a uniform fog, but a structured network shaped by gravity and time. Within this network, the story of cosmic history unfolds, setting the stage for all later developments. All across the sky, beyond the stars of the Milky Way, beyond the nearest galaxies and the most distant clusters, there is a faint glow that does not belong to any single object. It arrives from every direction. It does not come from stars, planets, or dust clouds in the usual sense. It is older than all of them in their present form. Scientists call it the cosmic microwave background. It is radiation, meaning energy carried through space as waves, and it fills the observable universe with remarkable uniformity. This glow is not bright to human sight. Its wavelengths are too long for the eye. It appears in the microwave part of the spectrum, stretched there by the expansion of space. Yet it is one of the clearest records of the early universe that science possesses. The cosmic microwave background is often described as ancient light, though by the time it reaches modern instruments it is no longer visible light. Long ago, when the universe is much hotter and denser than it is now, matter and radiation remain tightly linked. Electrons, which are light-charged particles, move freely rather than staying bound inside atoms. Protons, the positively charged particles in atomic nuclei, also move through the hot plasma. A plasma is a state of matter in which charged particles flow freely. In such a state, light cannot travel far without colliding with these particles. The universe is not dark in the ordinary sense during that era. It is full of radiation, but the radiation is trapped, scattered again and again in every direction. Space is more like a dense glowing fog than a clear window. As the universe expands, it cools. Cooling in this context does not mean that heat escapes into some outside region. It means that the energy within the expanding universe becomes spread over a growing volume, and the radiation stretches to longer wavelengths. Eventually, the temperature falls enough for electrons to join with protons and form neutral hydrogen atoms. A neutral atom has no net electric charge. Once this happens on a large scale, Light is no longer scattered so constantly by free electrons. The fog lifts. Radiation can travel much more freely. This event is known as recombination, though the name is slightly misleading because it marks the first stable formation of neutral atoms in cosmic history, rather than a repeated combination after an earlier neutral age. From that moment onward, much of the radiation streams across space largely unhindered. The cosmic microwave background is the surviving record of that release. It is not the light of the very beginning. It is the oldest light that can be directly observed because earlier than this, the universe remains opaque to ordinary radiation. This distinction matters. Scientists do not claim to see the first instant of the universe in the microwave background. They see a later stage, one that occurs about 380,000 years after cosmic expansion begins. In human terms, that is a span almost beyond imagination. In cosmic terms, it is still very early. The universe at that time contains no stars, no galaxies, no planets, no life. It contains mostly hydrogen and helium, along with dark matter, radiation, and slight differences in density that are already present across space. Those slight differences appear in the microwave background as tiny variations in temperature from one direction in the sky to another. The glow is extremely uniform, with an average temperature today of about 2.7 degrees above absolute zero. Absolute zero is the theoretical lowest temperature, where thermal motion reaches its minimum possible level. Against this nearly even background, the measured variations are only a few parts in 100,000. These differences are very small, yet they are of profound importance. They show that the early universe is not perfectly smooth. Some regions are slightly denser and slightly hotter, while others are slightly less dense and slightly cooler. These uneven patches provide the seeds from which later structure grows under gravity. The pattern of these variations is not random noise in the casual sense. It carries the imprint of physical conditions in the early universe. Before neutral atoms form, ordinary matter and radiation behave together like a fluid under pressure. Sound-like waves move through this hot plasma. These waves are not sound in empty space as heard by an ear. They are pressure oscillations, rhythmic compressions and rarefactions in the coupled matter and radiation. By measuring the size and distribution of the temperature variations in the cosmic microwave background, scientists can infer important properties of the universe, including its age, its overall geometry, and the amounts of ordinary matter, dark matter, and dark energy that shape cosmic history. This is one reason the microwave background holds such a central place in modern cosmology. It is not merely a relic glow, it is a precise physical record. Space missions and ground-based observatories have mapped this background with increasing accuracy. Measurements from NASA and ESA have shown that the radiation follows the spectrum expected from an almost perfect blackbody, meaning an ideal emitter of thermal radiation. This agreement is one of the strongest pieces of evidence that the early universe passes through a hot, dense state. The radiation does not look like the mixed light of stars. It has the smooth thermal character expected from a once uniform cosmic plasma. Even the tiny irregularities fit the broader model of a universe that expands and cools over time. There are also subtler features in this background. The radiation is slightly polarized in some regions, meaning the electric fields of the waves show preferred orientations created by scattering under early conditions. This polarization provides additional information about the state of matter and radiation at that time. It helps refine measurements of the early universe and supports the same broad picture. Observations also show that the cosmic microwave background is not perfectly still relative to Earth. One side of the sky appears a little warmer and the opposite side a little cooler because Earth, the solar system, and the Milky Way move relative to this cosmic rest frame. Once that motion is accounted for, the underlying uniformity becomes even more striking. Uncertainty remains in the finest details. Scientists continue to test small anomalies, rare patterns, and the exact implications of polarization and temperature statistics. Some observed features may be chance fluctuations within the standard model of cosmology. Others may hint at deeper physics. At present, the broad interpretation remains strong, while some details remain under active study. Observations indicate a hot early universe, a moment of release when neutral atoms form, and a relic radiation field that preserves the imprint of those conditions with extraordinary fidelity. This ancient glow exists long before any human mind is present to measure it. It fills all regions of the sky whether anyone watches or not. It passes silently through expanding space, cooling as the universe grows, carrying a memory not in words or symbols but in temperature, wavelength, and pattern. In this region of the story, the universe is not yet a place of stars and worlds. It is a cooling field of radiation emerging from a once opaque plasma, leaving behind a faint and nearly uniform light that still surrounds everything now. After the release of the ancient radiation that now fills the sky, the universe enters a long period marked by quiet change. The bright, dense fog of earlier times has thinned, and space becomes transparent. Light can travel across vast distances without constant scattering. The cosmic microwave background continues to move outward, stretching and cooling as space expands. In its wake, matter settles into a new state. The universe is now filled mostly with neutral hydrogen and helium atoms, along with dark matter that does not interact with light in the same way. There are no stars yet, no galaxies in their mature form. The universe is dim, not because light does not exist, but because there are no concentrated sources to illuminate space in the way stars will later do. This period is sometimes described as a dark age, though the term refers only to the absence of luminous objects rather than to any absolute darkness. Radiation still moves through space, including the relic glow from earlier times. However, that glow has cooled and shifted into wavelengths far from human sight. Ordinary matter, now in atomic form, drifts under the influence of gravity. The slight differences in density that appear in the cosmic microwave background begin to grow more distinct. Regions that are slightly denser exert a stronger gravitational pull. They attract nearby matter, drawing in gas and dark matter over long spans of time. The process is gradual. Gravity works without haste, yet it does not stop. As matter flows toward denser regions, those regions become denser still. This feedback leads to the formation of larger structures from small beginnings. The earliest concentrations of matter are not yet galaxies as they will later appear. They are more like growing clumps within the broader distribution of matter. Dark matter plays a central role in this stage. Because it does not interact strongly with radiation, it begins to collapse into structures earlier than ordinary matter can. It forms halos, extended regions of increased mass that create gravitational wells. Ordinary gas, made mostly of hydrogen and helium, falls into these wells. As gas collects, it begins to experience compression. Compression increases temperature. When gas is compressed by gravity, its particles move more rapidly, raising its thermal energy. However, the gas can also cool by emitting radiation. The balance between heating through compression and cooling through radiation determines how the gas behaves. In the early universe, cooling processes are less efficient than they will later become, because heavy elements are not yet present. Elements heavier than helium, which scientists call metals in this context, play an important role in cooling gas by providing more ways for energy to be radiated away. At this stage, such elements are absent or extremely rare. As a result, the gas must rely on simpler mechanisms, such as the emission from hydrogen molecules to shed energy. Despite these limitations, some regions manage to cool enough to contract further. As contraction continues, density increases, and the seeds of future stars begin to form. These early sites are small compared to later galaxies, but they mark the transition from a diffuse universe to one where localized structures can produce their own light. The timing of this transition is not a single moment across all space. It occurs at different times in different regions, depending on local conditions. Observations indicate that this process begins a few 100 million years after the cosmic microwave background is released, though exact details remain under study. While matter gathers, the large-scale pattern described as the cosmic web becomes more pronounced. Filaments grow denser, clusters begin to take shape, and voids expand as matter flows away from them. The distribution of matter becomes increasingly contrasted. Dense regions stand out more clearly against the sparse background. This evolution follows from the same initial variations seen in the microwave background, amplified over time by gravity. The universe is not static. It changes continuously, though the pace of change is measured in millions and billions of years. During this era, radiation still plays a role, though it no longer dominates the behavior of matter as it once does. The universe has shifted from a radiation-dominated state to one in which matter has greater influence over the dynamics of expansion and structure formation. This transition is part of the broader cooling and expansion of the cosmos. It allows gravity to shape matter more effectively, leading to the growth of increasingly complex structures. Uncertainty remains in the fine details of how the first luminous objects form. Observations of this era are challenging because the light from such distant times is faint and highly redshifted. Telescopes such as those operated by NASA and USA continue to push the limits of detection, revealing galaxies that existed when the universe is still young. These observations provide clues about the timing and nature of early structure formation, but they do not yet offer a complete picture. Models based on known physics help fill in the gaps, suggesting how gas behaves under the conditions present at the time. The universe in this region is quiet in a broad sense. There are no bright stars lighting the darkness yet, no complex chemistry beyond the simplest elements, no planets or life. Yet it is not empty or inactive. It is a stage of preparation. Matter is organizing itself under universal laws. Gravity draws, gas cools and contracts, and the first steps toward luminous structure begin to take place. The faint differences imprinted in earlier times are now growing into the foundations of everything that will later exist. Before humans, before any form of life, this period unfolds without observation or awareness. It is governed by the same physical principles that operate today, but expressed in a simpler environment. The absence of complex structures makes the processes more direct, easier to trace in theory, yet still vast in scale. Each region of slightly higher density becomes a focal point for future development. Over time, these regions will host the first sources of starlight, but at this stage, they remain dark, gathering matter and energy in preparation for what follows. The universe continues to expand throughout this period. Space stretches, distances grow, and the temperature of the background radiation decreases further. This expansion does not halt the formation of structure. Instead, it sets the stage within which structure forms, balancing the pull of gravity with the outward drift of space itself. The result is a universe that grows larger while simultaneously developing internal complexity. In this region, the story moves from a nearly uniform glow to a patterned distribution of matter that is beginning to organize into recognizable forms. It is a time defined not by visible brilliance, but by gradual accumulation and change. The quiet gathering of matter in darkness prepares the conditions necessary for the first light to appear, marking the next step inward in the unfolding of cosmic history. Within the growing concentrations of matter, the first true sources of starlight begin to appear. These are the earliest stars, forming from clouds of hydrogen and helium that have cooled and contracted under gravity. The process is gradual but decisive. Gas continues to fall inward toward the densest points within dark matter halos, and as it gathers, its temperature rises due to compression. When the density and temperature become high enough at the core of a collapsing cloud, nuclear fusion begins. Nuclear fusion is the process in which light atomic nuclei combine to form heavier nuclei, releasing energy in the form of radiation. With this ignition, a star is born. These first stars differ from many stars seen in the present universe. They form in an environment almost entirely free of heavier elements. Without these elements, cooling is less efficient, and gas clouds tend to fragment less. As a result, the earlier stars are thought to be more massive on average than many later stars. Observations indicate that massive stars burn their fuel quickly. They shine brightly and live short lives, lasting only a few million years before exhausting their nuclear fuel. Though direct observation of these very first stars remains difficult, models based on known physics support this general picture. The light from these stars begins to change the surrounding universe. Before their formation, space is filled with neutral hydrogen, which does not emit much visible light on its own. The radiation from the first stars is energetic enough to ionize this hydrogen, meaning it strips electrons away from atomic nuclei. This process creates regions of ionized gas around each star or group of stars. Over time, as more stars form, these regions grow and begin to overlap. The universe transitions from mostly neutral gas to a state where much of the hydrogen becomes ionized again. This transformation is known as reionization. Reionization does not occur all at once. It proceeds unevenly across space, depending on where stars and early galaxies form. Dense regions with many stars become ionized earlier, while more isolated regions remain neutral longer. Observations of distant quasars, which are bright sources powered by matter falling into supermassive black holes, show signs that by about 1 billion years after the beginning of cosmic expansion, much of the intergalactic hydrogen is ionized. It remains uncertain exactly how quickly this transition occurs and how much each type of early object contributes. Both stars and early galaxies play roles, and possibly other sources such as early black holes contribute as well. As stars form in increasing numbers, small galaxies begin to take shape. A galaxy is a system of stars, gas, dust, and dark matter bound together by gravity. The earliest galaxies are smaller and less structured than many seen today. They contain clusters of young stars and clouds of gas that continue to collapse and form new stars. Over time, these small galaxies can merge with one another, building larger systems. This process of merging is a key feature of galaxy evolution. It leads to the growth of more massive galaxies and the development of more complex structures within them. The radiation from early stars and galaxies not only ionizes gas but also heats it. This heating can influence the formation of later stars by preventing some gas from collapsing as easily. In this way, the first generation of stars affects the conditions for subsequent generations. the universe begins to develop a layered history, where earlier events shape the environment for later ones. Heavy elements, produced in the cores of massive stars and released when those stars end their lives in energetic events, begin to enrich the surrounding gas. These elements provide new pathways for cooling, allowing gas to fragment into smaller pieces and form stars of lower mass in later generations. The appearance of starlight marks a significant change in the universe. Regions that are no longer dark become sources of illumination. Light travels outward from these stars, crossing space and interacting with matter along the way. Some of this light eventually reaches observers billions of years later, carrying information about the conditions under which it is produced. Telescopes designed to observe very distant galaxies capture faint signals that have travelled for most of the age of the universe. These observations provide direct evidence of early star formation and galaxy assembly. Though they remain limited by the faintness and distance of the sources, uncertainty remains in the exact properties of the first stars. Their masses, lifetimes, and the details of their formation are inferred from theory and indirect evidence. Observations of later stars with very low metal content offer clues, as these stars may retain chemical signatures of earlier generations. Computer simulations continue to explore how gas behaves under the conditions present in the early universe, testing different scenarios and comparing them with observations. While the general picture of early star formation is well supported, many details are still being refined. The emergence of stars also introduces new physical processes into the cosmic environment. Radiation pressure, the force exerted by light, can push on surrounding gas. Stellar winds, streams of charged particles emitted by stars, can shape the interstellar medium. When massive stars reach the end of their lives, they can undergo powerful explosions known as supernovae, dispersing heavy elements and energy into space. These processes contribute to the dynamic evolution of galaxies and the intergalactic medium. In this region, the universe becomes a place of light and structure in a more familiar sense. The first stars and galaxies represent a transition from a simple distribution of matter to a complex system of interacting components. Gravity continues to guide the overall structure, but new forces and feedback processes emerge from the presence of luminous objects. The cosmic web now contains not only dark matter and diffuse gas, but also bright points of energy that alter their surroundings. Before any planet forms, before any chemistry more complex than simple atoms and ions develops in significant amounts, these early stars already burn and fade. Their brief existence leaves lasting effects, shaping the chemical and thermal state of the universe. The light they emit travels outward, joining the long history of radiation that fills space. In this way, the first stars begin to write a new layer into the story of the cosmos, one in which matter not only gathers but also shines. Beneath the visible pattern of galaxies and the light from early stars lies a deeper framework that does not shine. This framework is known as dark matter. It does not emit light, reflect it, or absorb it in a way that current instruments can detect directly. Its presence is inferred through gravity, the same force that shapes the motion of planets, stars, and galaxies. Observations indicate that the amount of this unseen matter exceeds the amount of ordinary matter by several times. Though invisible, it plays a central role in the structure and evolution of the universe. The evidence for dark matter emerges in several ways. Within galaxies, stars orbit the galactic center at speeds that cannot be explained by the gravity of visible matter alone. If only the observed stars and gas were present, outer stars would move more slowly than they do. Instead, their speeds remain high, suggesting additional mass distributed in a broad halo around the galaxy, in clusters of galaxies. The motion of galaxies within the cluster and the temperature of the hot gas between them also indicate more mass than can be accounted for by visible components. Gravitational lensing provides another line of evidence. Light from distant sources bends as it passes near massive objects. The amount of bending reveals the total mass, including the unseen part. In many cases, the inferred mass significantly exceeds what can be seen. Dark matter does not behave like ordinary matter in several key respects. It does not interact strongly with electromagnetic radiation. It does not form atoms, molecules, or solid structures. It does not cool by radiating energy in the same way gas does. As a result, it does not collapse into dense objects like stars or planets. Instead, it forms extended halos that surround galaxies and clusters. These halos provide the gravitational wells into which ordinary matter falls. In this sense, dark matter acts as a scaffold, shaping where visible structures can form. In the early universe, dark matter begins to clump together before ordinary matter can do so effectively. Because it does not interact with radiation, it is not held back by the pressure of the hot plasma that fills space in earlier times. As the universe expands and cools, dark matter gathers into regions of higher density, forming the seeds of future structure. Ordinary matter, once it becomes neutral and free to move without constant scattering by radiation, falls into these regions. The result is a layered structure in which dark matter defines the overall gravitational landscape, while ordinary matter collects within it to form stars and galaxies. Computer simulations that include dark matter produce large-scale patterns that closely resemble the observed cosmic web. Filaments and clusters arise naturally when dark matter evolves under gravity. These simulations start with initial conditions based on measurements of the cosmic microwave background. Over time, small density variations grow into the complex structures seen today. The agreement between simulation and observation provides strong support for the role of dark matter in cosmic evolution. While the exact nature of dark matter particles remains unknown, their gravitational influence is well established. Several candidates have been proposed to explain what dark matter might be. These include particles that interact very weakly with ordinary matter and radiation. Experiments on Earth attempt to detect such particles through rare interactions in sensitive detectors. Other observations look for indirect signs, such as radiation that might result from dark matter particles interacting with each other. So far, no direct detection has been confirmed. Observations indicate the presence of dark matter through its effects, but its composition remains uncertain. This uncertainty is one of the major open questions in modern physics. Dark matter also influences the formation of galaxies on smaller scales. The size and shape of dark matter halos affect how gas flows into them and how stars form. In some regions, feedback from stars and black holes can alter the distribution of gas, but the underlying dark matter structure remains dominant in setting the gravitational potential. The interaction between dark matter and ordinary matter leads to a rich variety of galaxy types and structures. Some galaxies are large and well organized, while others are small and irregular. These differences reflect both initial conditions and the ongoing interplay of processes within each halo. On the larger scales, dark matter contributes to the overall mass-energy content of the universe. Its gravitational influence affects the rate at which structures grow and the way the universe expands. Measurements of the cosmic microwave background, galaxy distributions, and gravitational lensing all help constrain the amount and distribution of dark matter. These measurements are consistent with the universe in which dark matter, makes up a significant portion of the total matter content. Despite its importance, dark matter remains elusive in a direct sense. It does not form visible objects, and it does not leave clear traces through light. Its presence must be inferred through careful observation and analysis of motion, structure, and gravitational effects. This indirect knowledge requires a combination of theory, simulation, and observation. Scientists test models against data, refine parameters, and search for new evidence that might reveal more about the nature of this unseen component. In this region of the cosmic story, the universe reveals that much of its structure depends on something that cannot be directly seen. The visible galaxies and stars trace the outlines of a deeper mass distribution. The cosmic web, with its filaments and clusters, follows the pattern set by dark matter. Without this hidden framework, the universe would look very different. Structures might form more slowly or not at all in the same way. Before humans, before any observation, this unseen mass shapes the evolution of the cosmos. It does so quietly, without emitting light or drawing attention to itself except through its effects. It guides the flow of matter, influences the birth of galaxies, and contributes to the overall balance of forces that govern cosmic expansion. In this way, dark matter stands as a reminder that not all of reality is accessible through direct perception. Some aspects must be understood through their influence on the things that can be seen. The study of dark matter continues, with new instruments and methods probing its properties. Observations become more precise, simulations more detailed, and experiments more sensitive. Each step brings a clearer picture of how this component fits into the broader framework of the universe. Yet the central mystery remains. What dark matter is made of is still unknown. Observations indicate its presence and its role, but the fundamental nature of this substance is an open question. In this layer of the universe, the visible and invisible combine to form a coherent whole. Light reveals the positions of stars and galaxies, while gravity reveals the mass that shapes their motion. Together, they describe a cosmos in which much of the structure rests on a foundation that cannot be directly observed, only inferred and understood through its effects. As the universe grows older and larger, another deep feature begins to stand out in the motion of everything across the largest scales. Space continues to expand, as earlier evidence already shows through the redshift of distant galaxies. For a long time, scientists expect that this expansion, once begun, should gradually slow under the pull of gravity. Matter attracts matter. Galaxies, clusters, gas, and dark matter all contribute to this attraction, even if the universe does not collapse. A reasonable expectation is that expansion should lose speed over time. Observations, however, reveal a different pattern. The expansion is not merely continuing. On the larger scales now measured, it is accelerating. This discovery does not mean that galaxies are pushing through space like objects fired outward by an explosion in ordinary air. It means that the scale of space itself changes in such a way that distant galaxies become separated from one another at an increasing rate. The evidence comes most clearly from observations of distant stellar explosions called Type I supernovae. These events occur when a white dwarf, a dense remnant of a star like the Sun, reaches a critical condition and undergoes a powerful thermonuclear explosion. Because these explosions tend to reach a similar intrinsic brightness, they can be used as standard candles. A standard candle is an object whose true brightness is known well enough that its observed brightness reveals its distance. By comparing the distances of these supernovae with the redshift of their host galaxies, Scientists find that faraway galaxies are farther than expected in a universe whose expansion is only slowing. The conclusion is that expansion has speeded up over cosmic time. This result is supported by other lines of evidence. Measurements of the cosmic microwave background show the overall geometry and contents of the universe in a way that, when combined with galaxy surveys, point to the same broad picture. The large-scale distribution of galaxies also preserves a preferred distance scale, a remnant of sound waves in the early universe, known as baryon acoustic oscillations. These patterns act as another cosmic ruler. When scientists compare this ruler across different eras of cosmic history, they again find evidence consistent with accelerated expansion. Observations from multiple methods therefore support the same conclusion. The universe on the largest scales is not simply coasting outward. Its expansion changes in a way that requires explanation. The name given to the unknown cause is dark energy. This term does not describe a substance that has been directly isolated in a laboratory. It is a label for whatever drives the observed acceleration. In the simplest model, dark energy behaves like a constant property of space itself. As space expands, this constant energy density does not thin out in the way ordinary matter does. Matter becomes more dilute as volume grows. Radiation becomes more dilute and also loses energy through the stretching of its wavelength. But a cosmological constant, which is the simplest mathematical form of dark energy, remains constant per unit volume. As more space exists, the total amount associated with that constant property becomes greater simply because there is more volume. In that picture, empty space is not truly empty. It carries a persistent energy that affects cosmic expansion. This idea has deep roots in general relativity. Einstein's equations allow a cosmological constant term, though its interpretation changes over time. Early in the history of modern cosmology, Einstein introduces such a term for reasons tied to a static universe, an idea later set aside after cosmic expansion is established. In present cosmology, a similar term returns in a different role, not to hold the universe fixed, but to explain why expansion accelerates. The mathematics works remarkably well. A universe containing ordinary matter, dark matter, radiation, and a cosmological constant fits a wide range of observations with impressive accuracy. Yet the physical meaning of this constant remains unsettled. Quantum theory, which describes fields and particles on small scales, appears to suggest a vacuum energy associated with empty space, but simple estimates from quantum physics differ enormously from the observed cosmic value. This mismatch is one of the most serious unresolved problems in theoretical physics. Other possibilities have been explored. Dark energy may not be strictly constant. It may evolve slowly over time, perhaps arising from a field that changes as the universe expands. Some proposals suggest that gravity itself behaves differently on the very largest scales, making the observed acceleration an apparent effect of incomplete theory rather than a new cosmic ingredient. Observations so far remain broadly consistent with the simplest explanation, a cosmological constant, but uncertainty persists. Scientists continue to test whether dark energy changes with time, or whether the laws of gravity require modification in extreme large-scale conditions. At present, the data do not compel a more complex model, though they do not close every question. As expansion accelerates, the large-scale future of the universe changes. Distant galaxies not gravitationally bound to the Milky Way and its nearby companions will move farther away. Over immense spans of time, more and more of the universe will slip beyond observational reach for any future astronomers inside our local group of galaxies. This does not happen because galaxies suddenly vanish, but because the expansion of space stretches the distance between large, unbound systems ever more rapidly. Light emitted in the far future by sufficiently distant galaxies will never reach observers in our region. The observable universe, in that sense, becomes lonelier with time even while space itself grows. This consequence belongs to the large-scale dynamics of expansion, and not to any change in the local structure of bound systems such as galaxies, solar systems, or planets. Gravity holds those local systems together against the weak effect of cosmic expansion on small scales. Dark energy therefore shapes not the interior of stars or the chemistry of planets, but the broad destiny of the universe. It governs the background against which all large-scale structure unfolds. Matter still gathers into galaxies and clusters where gravity is strong enough. But over the greatest distances, the accelerated expansion increasingly separates the major regions of the cosmos. In the earlier universe, matter dominates more strongly, and structure grows more efficiently. In the later universe, dark energy becomes more important because matter thins as space expands, while a cosmological constant does not. The balance shifts over time. This shift is one of the defining features of cosmic history. Before humans, before Earth, before the Sun, this outward tendency is already written into the behavior of the universe, though it becomes dominant only after billions of years. It is not visible in the ordinary sense. No one can look into the night sky and see dark energy directly. Its presence is inferred from distance, redshift, and the comparison of cosmic history across vast spans of time. It belongs to the deepest background of existence. A property or process that shapes the whole without announcing itself through light or sound. In this region of the story, the universe appears stranger than simple intuition expects. Gravity still acts, matter still gathers, yet the emptiness between the greater structures carries its own influence, and that influence changes the motion of the whole. Scientists can describe the effect with precision, test it against observation, and build models that match the sky. What they cannot yet say with confidence is why this effect exists in exactly this form. Observations indicate acceleration. It remains uncertain what dark energy fundamentally is. The universe therefore expands not only outward in distance, but also inward into mystery, with one of its broadest features resting on a cause still not fully understood. Moving inward through cosmic history, the universe becomes hotter, denser, and more uniform. The stars, galaxies, filaments, and voids of later ages no longer exist in any familiar sense. Even neutral atoms are gone. The earlier one looks, the less the universe resembles a structured landscape, and the more it resembles a single connected medium filled with radiation and particles in constant interaction. This is the hot, early universe, a stage in which matter and light are not separate realms but parts of one tightly coupled system. It is not yet a place of clear forms. It is a plasma, an energetic state in which charged particles move freely and collide continually. In this era, the temperature is so high that electrons cannot remain bound to atomic nuclei. Any neutral atom that tries to form is quickly broken apart by energetic photons, which are particles of light. The universe is therefore opaque to ordinary radiation. Light does not travel freely across great distances because it is scattered again and again by free electrons. This repeated scattering keeps radiation and ordinary matter in thermal contact. Thermal contact means that they exchange energy so efficiently that they share nearly the same temperature. The universe behaves like a glowing fluid, expanding and cooling while preserving an almost perfect large-scale uniformity. That uniformity is not exact. Tiny variations in density and temperature are already present, as later seen in the cosmic microwave background, but at this stage, those variations remain very small. The dominant impression is smoothness. There are no separate objects, no islands of matter surrounded by emptiness, no stars carving out light from darkness. The whole observable universe is filled with hot plasma, and every region participates in the same broad physical conditions: pressure, gravity, radiation, and expansion all operate together in a continuous medium. Radiation plays a much stronger role here than it does in later eras. In the younger universe, photons carry a large fraction of the total energy density. Because the universe is smaller, wavelengths are shorter, and temperatures are higher, matter exists. But radiation pressure has a major influence on how ordinary matter behaves. Pressure is the effect of particles or radiation pushing outward through motion and collision. In this hot plasma, radiation resists compression, while gravity works to draw denser regions inward. The interplay between these effects creates oscillations in the plasma, waves of compression and release that move through the early universe. These are the same pressure waves whose traces later appear in the temperature pattern of the cosmic microwave background and in the large-scale distribution of galaxies. The composition of the universe at this stage is simple compared with later cosmic history. Most ordinary matter consists of protons, electrons, and helium nuclei, along with a smaller amount of other light nuclei, neutrinos, which are extremely light particles that interact only weakly with matter, are also present in large numbers. Dark matter contributes gravitationally, but does not participate in the electromagnetic interactions that tie ordinary matter to radiation. Because of this difference, dark matter and ordinary matter do not evolve in exactly the same way. Ordinary matter is held in the glowing plasma, pushed and pulled by radiation pressure. Dark matter responds mainly to gravity, already beginning to gather into the deeper framework that will later guide visible structure. Time in this region is measured not in millions or billions of years but in much shorter intervals, though even then the physical changes are profound. As the universe expands, the average temperature falls. This cooling allows different transitions to occur. At first, the plasma remains too energetic for stable atoms. Later, as the temperature drops enough, electrons combine with nuclei and the universe becomes transparent. That later moment marks the release of the cosmic microwave background. But in the present layer of the story, that event has not yet taken place. The universe is still in the opaque phase, still glowing everywhere, still too hot for atomic stability. The scale of this environment is difficult to imagine because ordinary experience provides no close comparison. A flame, a furnace, or molten rock all depend on atoms and molecules retaining some structure. Here, those structures do not survive. Matter exists in a more stripped and fundamental state. The distinction between a region of gas and a region of light is less clear than it will later become, because the two remain deeply entangled through constant scattering. The universe is not empty space dotted with objects. It is a full and active medium whose properties are shared across immense distances. General relativity describes how the expansion of space proceeds in such a universe. The scale factor, which is a measure of how distances between unbound regions change with time, is smaller in the past and grows as the universe evolves. As it grows, the temperature of radiation drops. This relation between expansion and cooling is one of the central facts of early cosmology. It means that looking backward in time is also a movement toward greater density and energy. The farther inward one goes, The less room particles have, the more frequently they interact, and the more intense the thermal environment becomes. Observations strongly support this picture. The existence and properties of the cosmic microwave background show that the universe passes through an earlier opaque stage. The measured abundances of light elements also fit a hot early universe in which nuclear reactions occur under dense and energetic conditions. Large-scale structure, when traced backward through physical models, points to a time before galaxies exist, when matter and radiation fill space in a much smoother form. This does not mean every detail is settled. Some questions remain about the exact behavior of different components, the role of possible new particles, and the finest features of early fluctuations. Yet the broad framework is well established. The universe becomes hotter, denser, and more uniform as one goes back into this plasma age. Before humans, before Earth, before stars, before neutral atoms, there is this radiant state. It is not silent in a literal sense, because sound as pressure waves can move through a plasma, though there are no ears and no atmosphere in the ordinary planetary sense to receive it. More importantly, it is dynamic. Waves pass through the coupled matter and radiation. Density rises and falls slightly from place to place. Particles collide endlessly. Expansion stretches the whole while heat slowly declines. The universe is alive with process, though it contains none of the structures later associated with life. In this region, the question of what existed before humans receives a severe and impersonal answer. Before bone, before cell, before ocean, before planet. The universe is a hot, luminous plasma with no surface and no center that matters physically. It is governed by temperature, pressure, gravity, and expansion. It does not resemble a world waiting for inhabitants. It is a physical state of extraordinary simplicity and power, one in which the ingredients of later history remain present but unassembled. Matter has not yet settled into atoms. Light has not yet been released to travel freely. The cosmos exists as a dense and radiant whole, still carrying the conditions from which later structure will slowly emerge. As the universe continues to be traced inward in time, the temperature rises further, and the conditions become suitable for a brief but significant process, the formation of the first atomic nuclei. This stage is known as primordial nucleosynthesis. It occurs within the first few minutes after cosmic expansion begins. Before this point, the universe is too hot for nuclei to remain stable. Protons and neutrons, the building blocks of atomic nuclei, exist but cannot combine without being immediately broken apart by energetic radiation. As expansion proceeds, the temperature falls to a level where nuclear reactions can begin to produce lasting combinations. Protons are positively charged particles that will later form the nuclei of hydrogen atoms. Neutrons carry no electric charge and can combine with protons to form heavier nuclei. In the earliest moments, protons and neutrons are in a state of rapid interaction, converting into each other through weak nuclear processes. The balance between them depends on temperature and the rate of expansion. As the universe cools, this balance shifts, and the number of neutrons relative to protons begins to decrease. Some neutrons decay into protons, electrons, and neutrinos, since free neutrons are not stable over long periods. When conditions become suitable for nuclei to form, protons and neutrons begin to bind together through the strong nuclear force. The strong nuclear force is the interaction that holds atomic nuclei together, despite the electrical repulsion between positively charged protons. The simplest bound state is deuterium, which consists of one proton and one neutron. Deuterium acts as a stepping stone for the formation of slightly heavier nuclei. Once deuterium becomes stable in sufficient amounts, it can fuse into helium and trace amounts of other light elements. This process does not continue indefinitely. It is limited by both temperature and density. If the temperature is too high, newly formed nuclei are broken apart by energetic photons. If the temperature drops too low, nuclear reactions slow and eventually stop because particles no longer collide with enough energy to overcome repulsive forces. There is therefore a narrow window in which primordial nucleosynthesis can occur efficiently. During this window, the universe produces a mixture of light nuclei dominated by hydrogen and helium, with very small amounts of deuterium, helium with one fewer neutron, and traces of lithium. Observations of the present universe provide strong support for this process. The relative abundance of helium, for example, is about 1/4 of ordinary matter by mass, with hydrogen making up most of the remainder. These proportions are consistent with predictions based on a hot early universe undergoing nucleosynthesis under known physical laws. Measurements of deuterium in distant gas clouds also match the expected values from this process, making deuterium an important indicator of early conditions. The agreement between theory and observation is one of the key successes of modern cosmology. At this stage, the universe is still a hot plasma. Nuclei exist, but electrons remain unbound due to the high temperature. There are no atoms yet, only a mixture of charged particles and radiation in constant interaction. The presence of helium nuclei marks a shift in composition, but it does not yet produce the chemistry seen in later eras. Chemical behavior depends on atoms and molecules, which require lower temperatures and stable electron orbits. Here, the focus remains on nuclear physics, the formation of the cores that will later become the centers of atoms. The process of nucleosynthesis is sensitive to the rate of expansion of the universe. If expansion occurs more rapidly, there is less time for nuclear reactions, and the resulting composition differs. If expansion is slower, more reactions can occur before conditions cool too much. Observations indicate that the expansion rate during this early period aligns with predictions from the broader cosmological model. This agreement supports the idea that the same framework describing expansion and gravity applies consistently from these early times to the present. Neutrinos also play a role during this era. These particles interact very weakly with matter, but their abundance and behavior influence the energy balance of the universe. As the universe expands and cools, neutrinos decouple from other particles, meaning they begin to move freely without frequent interaction. Though difficult to detect directly, their presence affects the outcomes of nucleosynthesis and the evolution of early conditions. Measurements of cosmic background radiation and other observations provide indirect evidence for their influence. Despite the success of the model, some uncertainties remain. The exact amount of lithium produced in primordial nucleosynthesis appears to differ from what is observed in certain ancient stars. This discrepancy, known as the lithium problem, is an area of ongoing research. It may reflect gaps in understanding of nuclear reaction rates, stellar processes that alter lithium after formation, or new physics beyond the standard model. While the overall picture of nucleosynthesis is well supported, this detail remains unresolved. The universe at this stage is still extremely simple compared to later epochs. It contains mostly hydrogen and helium nuclei, free electrons, radiation, neutrinos, and dark matter. There are no stars, no galaxies, no planets. The entire observable region is filled with a hot, dense plasma in which nuclear reactions briefly shape the composition of matter. Once the temperature falls below the threshold for further fusion, the composition becomes largely fixed. The universe carries this mixture forward into later stages, where atoms will eventually form and structure will begin to grow. Before humans, before any complex form of matter, this brief period determines the basic ingredients of the cosmos. The hydrogen that will later form stars and fuel their fusion processes is set in place. The helium that will accumulate in stellar cores is already present. These elements will participate in countless future events, from the formation of galaxies to the creation of heavier elements within stars. The outcome of these early minutes therefore influences the entire later history of the universe. In this region, the answer to what existed before humans becomes even more stripped of familiar reference. There are no objects in the ordinary sense, only particles and forces interacting under extreme conditions. The universe is governed by nuclear reactions and rapid expansion. It is not yet a place of light sources or structure, but a stage in which the fundamental composition of matter is established. Observations indicate that this stage occurs, and its results are still visible today in the distribution of elements across the cosmos. What remains uncertain are the finer details, the small discrepancies, and the deeper reasons behind the precise values observed. The formation of the first nuclei marks a transition from a state where even these basic structures cannot survive to one where they can persist. It is a short but decisive interval, setting the chemical baseline for everything that follows. Beyond this point, the universe will continue to cool, allowing new forms of organization to appear, but the elemental foundation laid here will remain a constant presence throughout cosmic history. Continuing further inward, the universe reaches conditions where even atomic nuclei cannot yet exist. The temperature rises to such an extent that protons and neutrons themselves cannot remain bound states. Instead, the universe is filled with their more fundamental constituents, quarks and gluons. Quarks are elementary particles that combine to form protons and neutrons, while gluons are the carriers of the strong force that binds quarks together. Under ordinary conditions, quarks are never found in isolation. They are confined within composite particles such as protons and neutrons. In this earlier state, however, confinement has not yet taken hold. The energy density is so high that quarks and gluons move freely in a dense, interacting medium known as a quark-gluon plasma. This plasma is not a gas in the familiar sense. It is a state of matter defined by extreme temperature and density, where interactions between particles are constant and intense. The distinction between individual particles becomes less meaningful than in cooler environments. Quarks exchange gluons rapidly, and the entire system behaves as a strongly coupled fluid. Experiments conducted in particle accelerators on Earth, such as those at facilities operated by CERN, have recreated small and short-lived regions of quark-gluon plasma. These experiments provide insight into how such a state behaves, though the early universe contains it on a far larger scale. As the universe expands, the temperature decreases. This cooling leads to a transition known as hadronization. During this transition, quarks and gluons become confined within composite particles. Protons and neutrons emerge as stable bound states. This change is not instantaneous but occurs over a range of conditions as the energy density falls below a critical level. Once confinement takes place, the quark-gluon plasma gives way to a universe filled with hadrons, which are particles made of quarks bound together. Protons and neutrons are the most important hadrons for later cosmic evolution. The physics governing this transition is described by quantum chromodynamics, the theory of the strong interaction. This theory explains how quarks interact through gluons and how confinement arises at lower energies, while the equations of quantum chromodynamics are well established. Solving them exactly under all conditions remains difficult. Numerical methods and experiments help to explore the behavior of matter in this regime. Observations of high-energy collisions support the idea that a quark-gluon plasma exists under extreme conditions, and that it transitions to confined matter as energy decreases. During this stage, the universe is still extremely small compared to its later size. Distances between particles are tiny, and interactions occur on timescales far shorter than those associated with later cosmic events. The concept of temperature is tied to the average energy of particles, which is extraordinarily high. The density of energy is also immense, meaning that even a small region contains a vast amount of energy compared to everyday experience. Gravity, while present, does not dominate local interactions in the same way it does on larger scales. Instead, the strong and weak nuclear forces, along with electromagnetic interactions, govern the behavior of particles. The composition of the universe at this stage includes quarks of different types, gluons, leptons such as electrons and neutrinos, and photons. Leptons are particles that do not participate in the strong interaction. They move freely through the plasma, interacting through other forces. Neutrinos, in particular, interact very weakly and begin to decouple from the rest of the matter at slightly later times. The balance between these different components influences the evolution of the universe as it continues to expand and cool. As hadronization proceeds, the universe transitions into a state where protons and neutrons exist as distinct entities. This change sets the stage for the later formation of atomic nuclei during primordial nucleosynthesis. The number of protons and neutrons present, and their ratio, are determined by processes that occur around this time, including interactions governed by the weak nuclear force. These processes establish the initial conditions for the formation of light elements in the next stage of cosmic history. Observations do not allow direct viewing of this era, as the universe remains opaque to electromagnetic radiation. Instead, knowledge of this stage comes from a combination of theoretical physics and experimental results obtained under controlled conditions. Particle accelerators provide a way to study high-energy interactions that approximate those in the early universe, though only for extremely short durations and small volumes. The consistency between these experiments and the theoretical framework gives confidence in the general picture. Even as details continue to be refined, uncertainty remains in certain aspects of this transition. The exact nature of the quark-gluon plasma, its properties under different conditions, and the precise details of the confinement process are areas of active research. There may also be additional particles or interactions that have not yet been observed, which could influence behavior at these energies. Scientists continue to explore these possibilities through both experimental and theoretical work. In this region, the universe is stripped down to a level even more fundamental than atomic nuclei. It is a realm where the familiar building blocks of matter have not yet assembled into stable forms. Instead, matter exists as a dynamic and densely interacting field of elementary particles. The processes that occur here determine how those particles will later combine into the protons and neutrons that form the basis of all visible matter. Before humans, before stars, before atoms, even before nuclei, the universe passes through this state of free quarks and gluons. It is a stage defined by extreme conditions and rapid transitions. The laws of physics that govern it are consistent with those observed today, yet they operate in a regime far removed from everyday experience. The existence of this phase is supported by both theory and experiment. though it cannot be directly observed in its original cosmic context. This layer of the universe reveals that the deeper one goes into the past, the less structure remains in the ordinary sense. Matter becomes more uniform, interactions more fundamental, and distinctions between forms less pronounced. The emergence of protons and neutrons from this plasma marks a key step toward the formation of the material world as it is later known. It is a transition from a state of free constituents to one of bound structures, setting the foundation for all subsequent complexity. Moving further inward, the universe approaches conditions where even the familiar distinctions between forces and particle types begin to blur. At lower energies, the universe is described by several fundamental interactions: the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity. These forces appear separate in their effects and in the particles that carry them. In earlier and hotter conditions, however, some of these distinctions are no longer present in the same way. The universe passes through stages in which symmetries, meaning underlying similarities in physical laws, are more complete than they are at later times. A symmetry in physics refers to a property of a system that remains unchanged under certain transformations. In the context of the early universe, symmetries can connect forces and particles that later appear distinct. As the universe cools, these symmetries break. Symmetry breaking does not mean that a law is destroyed. It means that the conditions of the system change in such a way that the full symmetry is no longer visible in the behavior of particles. A simple analogy is a perfectly smooth surface that becomes patterned as it cools or changes state. The underlying rules remain, but the visible form changes. One of the most important symmetry transitions involves the electromagnetic force and the weak nuclear force. At high energies, these two forces are unified into a single interaction known as the electroweak force. In this unified state, the carriers of these forces behave as part of one system. As the universe expands and cools, this symmetry breaks. The electroweak force separates into the electromagnetic force, which governs interactions involving electric charge and light, and the weak force, which governs certain types of particle decay and transformation. This separation gives rise to distinct particles that carry these forces, such as photons for electromagnetism and other heavier particles for the weak interaction. The mechanism behind this separation is associated with a field known as the Higgs field. A field in physics is something that has a value at every point in space. The Higgs field acquires a non-zero value as the universe cools below a certain temperature. This change affects how particles acquire mass. Before this transition, many particles are effectively massless, meaning they move at the speed of light and cannot form stable bound states in the usual way. After the Higgs field settles into its new state, particles interact with it in such a way that they gain mass. This process allows for the formation of more complex structures in later stages of the universe. The timing of this symmetry breaking occurs at extremely high temperatures, far beyond those encountered in any natural environment today. Particle accelerators can probe aspects of this physics by reaching high energies in collisions, providing evidence for the existence of the Higgs boson, a particle associated with the Higgs field. The discovery of this particle supports the theoretical framework describing how particles acquire mass and how the electroweak symmetry is broken. While the conditions in accelerators are not identical to those of the early universe, they offer a window into the same underlying principles. In addition to the electroweak transition, other possible symmetry relationships are studied in theoretical physics. Some models suggest that at even higher energies, the strong nuclear force may unify with the electroweak force into a single interaction. These ideas are part of what are called grand unified theories. Observations so far do not confirm such unification directly, and it remains uncertain whether these symmetries exist in nature. However, they provide a framework for thinking about how the forces might be connected at deeper levels. During this stage, the universe is still extremely hot and dense. Particles and radiation are in constant interaction, and the concept of individual objects does not apply. Instead, the universe is described in terms of fields and their excitations. An excitation of a field is what is observed as a particle. The distinction between particle and field becomes less intuitive than in everyday experience, as both are aspects of the same underlying description. The behavior of these fields determines how energy and matter evolve as the universe expands. The breaking of symmetries has lasting consequences. Once the forces separate and particles acquire mass, the pathways for later processes become defined. The formation of protons and neutrons, the creation of atomic nuclei, and the eventual emergence of atoms all depend on the properties established during these transitions. Small differences in how symmetries break could lead to a universe with very different characteristics. Observations indicate that the laws and constants governing these processes take the values that allow the universe to develop the structures seen today, though the deeper reasons for these specific values remain an open question. Uncertainty persists in several areas related to this stage. While the electroweak theory is well supported by experiment, the full behavior of fields at extremely high energies is not completely known. The possibility of additional particles or interactions beyond the standard model is actively explored. Such additions could alter the details of symmetry breaking or introduce new phases in the early universe. Experiments continue to test these ideas, searching for deviations from established predictions. In this region, the universe is governed by a set of principles that are both elegant and abstract. The separation of forces and the emergence of mass are not events that can be directly observed in the cosmos today. They are inferred from theory and supported by high-energy experiments. These processes occur at a level deeper than the formation of matter as it is commonly understood. They shape the rules by which particles interact, setting the stage for all subsequent structure. Before humans, before atoms, before even protons and neutrons exist as stable entities, the universe passes through this phase of symmetry and its breaking. It is a stage where the differences between forces are not yet fixed, where particles move without mass in the usual sense, and where fields determine the behavior of all components. The transition from this state to one with distinct forces and massive particles is a key step in the evolution of the universe. This layer reveals that the fundamental properties of matter and interaction are not static features present from the very beginning in their final form. They emerge through changes in the state of the universe as it cools and expands. The laws themselves remain consistent, but their expression changes with conditions. The breaking of symmetry is therefore not a loss, but a transformation that allows complexity to arise from a simpler underlying order. Further inward, the universe reaches one of the earliest intervals that scientists can discuss in a structured way, without claiming certainty where none exists. This is the region associated with inflation, a proposed period of extremely rapid expansion in the very young universe. Inflation is not the ordinary long-term expansion observed today. It is a brief and extraordinary episode in which space itself may grow at an enormous rate, smoothing and stretching the young cosmos in a fraction of a second. The idea is not introduced for dramatic effect. It is studied because it helps explain several otherwise puzzling features of the observable universe. One of those features is large-scale uniformity. Regions of the universe that are now widely separated appear remarkably similar in temperature and general properties, especially in the cosmic microwave background. Without some earlier mechanism, it is difficult to explain how these distant regions come into such close agreement, because light and other signals do not appear to have enough time to pass between them under simple expansion alone. Inflation offers a possible answer. If the observable universe begins as a much smaller region that is already in causal contact, meaning its parts can influence one another, and then that region undergoes a burst of rapid expansion, the smoothness seen later becomes easier to understand. In that picture, the wide uniformity of the present sky reflects the earlier closeness of regions that are now far apart. Inflation also helps explain why the geometry of space appears so close to flat on the largest observable scales. In ordinary geometry, a flat surface is one in which parallel lines remain parallel and the angles of a triangle add to 180 degrees. In cosmology, flatness refers to the large-scale curvature of space. Observations indicate that this curvature is very small, if it exists at all within the observable universe. Inflation can account for this by stretching any initial curvature so strongly that the observable region comes to look nearly flat, much as a small patch on a very large curved surface can appear almost perfectly level. A third important feature concerns the small irregularities from which later structure grows. The early universe is smooth, but not perfectly smooth. Tiny fluctuations in density and temperature are present. Inflation provides a possible origin for these fluctuations through quantum effects. Quantum fluctuations are extremely small temporary variations associated with fields at microscopic scales. In an ordinary setting, such fluctuations remain tiny. During inflation, however, the rapid stretching of space may enlarge them from subatomic scales to cosmic scales. Once stretched, these variations can become frozen into the structure of the young universe. Later, gravity amplifies them, turning slight differences in density into the seeds of galaxies, clusters, and the cosmic web. In this way, the largest known structures may trace their origin to very small fluctuations in an early field. The mechanism behind inflation is not settled with certainty. Many models describe it through a field that temporarily dominates the energy density of the universe. In some versions, this field sits in a high-energy state that drives rapid expansion. As the field changes and loses that energy, inflation ends, and its stored energy is transferred into particles and radiation, filling the universe with the hot contents that later evolve through the stages already described. This transition is often called reheating, though the term can oversimplify a process that remains under active study. What matters in the broad picture is that inflation, if it occurs, must end in a way that leads into the known hot early universe supported by observations. Evidence for inflation is indirect. Scientists do not observe inflation itself in a direct and final manner. Instead, they test whether the consequences predicted by inflation match the sky. The broad smoothness of the universe, the near flatness of space, and the pattern of fluctuations seen in the cosmic microwave background are all consistent with inflationary ideas. The observed fluctuations are nearly scale invariant, meaning their strength changes only slightly across different size scales, and this is close to what many inflation models predict. The fluctuations also appear close to Gaussian, meaning their statistical distribution follows a simple bell-like pattern with only small deviations. These features make inflation an attractive framework, yet uncertainty remains. Inflation is a family of models rather than a single completed theory. Different versions propose different fields, different energy scales, and different ways for inflation to begin and end. Some models predict a background of primordial gravitational waves, which are ripples in space-time generated in the early universe. Detecting a clear sign of such waves in the polarization pattern of the cosmic microwave background would strongly support certain versions of inflation. So far, no unambiguous detection has been confirmed. Observations place important limits, but they do not yet single out one model beyond dispute. It remains uncertain whether inflation occurs exactly as many theories describe, whether it takes a somewhat different form, or whether some alternative explanation may account for the same observations. This region therefore stands at the frontier between well-supported cosmological history and deeper theoretical reconstruction. The hot early universe after inflation is strongly supported by several lines of evidence. Inflation itself is a powerful and widely studied explanation for how the conditions of that hot universe come to be arranged. It is not established in the same direct way as the expansion of the universe or the existence of the cosmic microwave background, but it is supported by how naturally it addresses several major features of the observable cosmos. Before humans, before stars, before atoms, before nuclei, before the plasma ages already described, there may be this brief interval in which space expands with astonishing rapidity. If so, it is an era in which the universe becomes smoother on large scales while also acquiring the tiny irregularities that later grow into all visible structure. It is a paradox only in appearance. The same process that flattens and evens the cosmos may also preserve minute variations by stretching them into lasting patterns. The later universe, with its galaxies and voids, may therefore carry the magnified imprint of quantum behavior from this very early stage. In this layer, the answer to what existed before humans becomes even less familiar to ordinary thought. There are no objects, no chemistry, no light sources, and perhaps not even a stable hot plasma yet in the later sense. There may instead be a field-dominated phase in which the geometry of space changes at an extreme rate, and microscopic fluctuations are drawn outward into cosmic significance. Observations indicate that the present universe contains traces consistent with such a beginning. It remains uncertain exactly what drives inflation, how it starts, and whether the simplest inflationary stories are fully correct. Still, this region offers one of the most compelling attempts to connect the smooth large-scale universe to the tiny variations from which all later structure grows. Further inward, the path reaches a boundary where current physics loses its ordinary grip. This is often called the Planck boundary, not because science finds a physical wall there, but because known theories no longer join together reliably under those conditions. The name comes from the Planck scale, a set of units built from fundamental constants of nature. At this scale, the effects of quantum theory and gravity are both expected to be strong at the same time. Quantum theory describes the behavior of matter and fields on very small scales. General relativity describes gravity and the large-scale structure of space-time. Each theory works extraordinarily well in its own domain. The problem is that they do not yet combine into one complete description of reality under the most extreme early conditions. As one approaches this boundary in thought, the universe becomes so hot, dense, and compact that the curvature of space-time itself is no longer a smooth background on which particles merely move. In general relativity, matter and energy tell space-time how to curve, and curved space-time tells matter how to move. In ordinary cosmic evolution, this framework remains powerful and precise, yet quantum theory suggests that at sufficiently small scales, physical quantities can fluctuate. If those fluctuations apply not only to particles and fields within space-time but to space-time itself, then the smooth geometry assumed by general relativity may no longer hold. instead of a clean and continuous arena, the structure of space and time may become subject to deep uncertainty. This is the central difficulty. General relativity treats gravity as geometry. Quantum theory treats interactions in terms of fields, probabilities, and discrete processes. When the universe is traced back to a state of enormous density, both viewpoints become necessary. Yet no final accepted theory unites them in a way that has been confirmed by experiment. Scientists can calculate successfully in many extreme situations, but the earliest fraction of a second pushes existing tools beyond their tested range. The equations that describe expansion can be extended backward only so far before they suggest a singularity. A singularity is a point where quantities such as density and curvature become formally infinite within the mathematics. In physical terms, such infinities are often understood as signs that a theory has reached the limit of its applicability, rather than that nature literally contains an object with infinite density in a simple sense. This distinction matters. When current equations imply a singularity at the beginning of cosmic expansion, scientists do not all interpret that result as a direct picture of what reality must be. Many interpret it as evidence that classical general relativity is incomplete under those conditions. Observations strongly support an early hot and dense universe. They do not directly show that reality begins from a mathematical point of infinite density. The Planck boundary therefore marks a region where careful language becomes essential. Science does not end there, but certainty does. Extrapolation continues only with caution. The Planck time, an extremely small interval after the beginning of expansion in standard calculations, is often used as a symbolic marker for this limit. Earlier than that interval, the known equations are not trusted in a complete way. This does not mean that nothing can be said. It means that what can be said becomes more dependent on speculative theory. Some approaches to quantum gravity attempt to describe this regime. Quantum gravity is the general name for efforts to unify gravity with quantum principles. These efforts include string theory, loop quantum gravity, and other frameworks, each with its own mathematical structure and physical interpretation. None has yet achieved decisive experimental confirmation as the correct description of nature. In some proposed pictures, space-time at the smallest scales is not smooth but has a granular or quantized character. In others, fundamental objects are not point particles but extended entities, and the familiar geometry of space emerges only at larger scales. Some models suggest that the universe avoids a true singularity through a bounce, in which an earlier contracting phase gives way to expansion. Others suggest that the beginning is not a singular event in ordinary time at all, but a transition from a more abstract quantum state. These ideas are studied seriously, but at present they remain unconfirmed. Observations indicate that the later universe expands from a very hot, dense state. It remains uncertain what exact physical description applies at the Planck boundary itself. The challenge is not only experimental but conceptual. Time, as normally understood, may not behave in an ordinary way under these conditions. In general relativity, time is woven into space-time and shaped by gravity. In quantum theory, the treatment of time is different, usually more fixed in the background of calculations. A full quantum theory of gravity may require a revised understanding of time altogether. Some models imply that familiar time emerges from a deeper structure rather than existing in the same way at the earliest stage. If so, asking what happens at the Planck boundary may already strain language built for later and calmer parts of the universe. Even so, the Planck boundary is not a place of complete ignorance. It is reached through a sequence of increasingly well-supported layers. the expansion of the universe, the cosmic microwave background, the abundance of light elements, the growth of large-scale structure, the behavior of high-energy particles, and the role of quantum fields all point inward toward conditions of enormous energy and compression. Each outer layer narrows the range of plausible inner explanations. Scientists do not know exactly what the earliest physically meaningful description is, but they know that it must connect smoothly enough to the tested universe that follows. Any successful theory must reproduce the known hot early universe and lead naturally to the later history already observed. Before humans, before stars, before atoms, before nuclei, before quarks are confined into protons and neutrons, there may be this threshold where the distinction between geometry and matter becomes unstable. The universe is no longer describable as a set of particles moving through a stable space. Space itself may participate in quantum uncertainty. Distance and duration may lose their familiar meaning. The ordinary language of before and after begins to thin. What exists in this region may not resemble any object, medium, or field, as later physics describes them separately. It may instead be a domain where the categories used in later science are only partly formed. In this layer of the story, the answer to what existed before humans becomes more severe and more careful. Not only is there no life or planet or star, there may not even be a smooth stage on which such things could eventually appear. There is a limit to present knowledge, and that limit is not caused by lack of effort. It comes from the unfinished state of fundamental theory. Observations indicate that the universe once occupies conditions so extreme that current laws, taken separately, are insufficient. It remains uncertain whether the earliest meaningful description is a singular beginning, a bounce, an emergent geometry, or something not yet conceived. The Planck boundary is therefore less a final answer than a disciplined stopping point, where science remains grounded by admitting exactly where its deepest successful models begin to blur. Beyond the Planck boundary, the language of ordinary sequence becomes uncertain. In the outer regions of the story, time behaves in a way that allows clear order. The universe cools, structures form, radiation travels, matter gathers. Even in very early stages, one can still speak meaningfully of before and after, because physical models preserve a workable timeline. Here, near the deepest inward limit of present theory, that certainty begins to loosen. Scientists can still ask whether time itself has a beginning, but the question becomes harder to frame with precision. The difficulty is not only that evidence is scarce, it is that time may not exist in the same form under such extreme conditions as it does in the later universe. In everyday life, time appears as a continuous flow. Events occur in sequence. Causes come before effects. Motion unfolds through duration. Modern physics preserves much of this order, but it also changes the picture. In relativity, time is bound together with space in a single structure called space-time. The rate at which time passes depends on motion and gravity. Time is not a universal river moving identically everywhere. It is part of the geometry of the universe. In quantum theory, time is often treated differently, more as a fixed background against which probabilities evolve. These two successful ways of describing nature already place time in somewhat different roles. At the earlier stage of the universe, where gravity and quantum behavior must both matter strongly, the tension between these descriptions becomes impossible to ignore. One possible conclusion is that ordinary time begins with the hot expanding universe itself. In this view, asking what comes before the beginning may be like asking what lies north of the North Pole. The question uses familiar directional language beyond the domain where it applies. If time is part of the universe rather than a container outside it, then there may be no earlier temporal region in the usual sense. There may be a boundary, not in space, but in the meaningful extension of classical time backward. Some proposals in theoretical physics express this idea by replacing the singular beginning with a smoother mathematical condition, in which the ordinary distinction between time-like and space-like directions changes near the origin. In such models, the beginning is not a sharp explosion from nothing in a dramatic physical sense, but a limit where familiar time emerges from a more primitive or more abstract state. Another possibility is that time, in some form, extends beyond the earliest hot expanding phase. In bounce models, for example, the universe does not begin from a one-way origin, but passes through a transition from contraction to expansion. The expanding universe known today is then preceded by an earlier contracting state. This idea can avoid a singular beginning in some frameworks, though it faces serious theoretical challenges and remains unconfirmed. The difficulty is not merely to invent a prior stage, but to describe it in a mathematically consistent way that also reproduces the well-tested universe observed later. Some models can do this in part. None has yet achieved decisive empirical confirmation. There are also approaches in which time is emergent. In such views, time is not fundamental at the deepest level. It appears only when a more basic underlying reality organizes itself in a certain way. This idea may seem abstract, yet physics already contains examples where familiar large-scale behavior emerges from deeper processes. Temperature emerges from the motion of many particles rather than existing as a property of one isolated particle. A fluid emerges from countless molecules. In a somewhat similar spirit, some researchers explore whether time itself could emerge from more fundamental relationships, quantum states, or informational structures. If so, then what exists before ordinary time may not be a previous moment at all. It may be a non-temporal structure from which temporal order later arises. These ideas remain speculative. Observations strongly support a hot early universe, cosmic expansion, and the later history that follows. They do not yet determine whether time begins absolutely, whether it extends through a prior phase, or whether it emerges from something deeper. The cosmic microwave background, the distribution of galaxies, and the abundances of light elements all constrain what the early universe becomes by the time-tested physics applies. They do not directly reveal whether the word before has a valid meaning at the deepest boundary. This is one of the places where scientific honesty requires restraint. There are models, arguments, and mathematical possibilities. There is not yet a confirmed final answer. Even the concept of nothing becomes delicate in this region. In ordinary language, nothing suggests the absence of everything. In physics, the term is often used more loosely and can cause confusion. A quantum vacuum, for example, is not simple non-existence. It is a physical state with structure, laws, and possible fluctuations. If one says the universe arises from a quantum vacuum, one is not describing creation from philosophical nothingness. One is describing emergence from a particular physical condition governed by rules. This distinction matters because many statements about cosmic beginnings sound more final than they are. Scientific models describe physical states and transitions. They do not automatically answer why there are laws at all, or why there is a framework capable of producing a universe. In this region, the deepest caution is also the deepest clarity. Science can say that the familiar timeline of the universe reaches backward to an extremely early hot phase. It can say that known theories become incomplete at still earlier conditions. It can propose that time may begin there, or that it may continue in some transformed manner, or that it may emerge from a deeper order. It cannot yet decide among these possibilities with confidence. Observations indicate a beginning to the observable expansion history. It remains uncertain whether this corresponds to the absolute beginning of time. Before humans, before life, before stars, before atoms, before even the plasma ages of the young universe, there may be no before in the human sense, or there may be a prior physical reality whose form is so unlike later cosmic conditions that ordinary time words barely apply. This is not a place for fear in the dramatic sense. It is a place where intuition becomes too small. The human mind, shaped by seasons, days, motion, and memory, tries to carry its usual grammar into a domain where grammar itself may fail. Yet science still advances by marking that failure precisely. It narrows the unknown, defines the boundary, and distinguishes what is measured from what is imagined. So in this near-final inward layer, what existed before humans is no longer merely ancient matter or radiant plasma. It may involve the very coming into being of time as a meaningful physical feature. The universe may not have waited inside an earlier empty duration. Duration itself may belong to the universe and arise with it. Or perhaps some deeper physical order precedes the timeline now known. For the moment, the evidence does not close the question. It leaves a disciplined uncertainty, one that is smaller than myth and larger than certainty, resting at the threshold where science can still speak, but only with care. At the deepest inward reach of the story, all the outer layers can now be gathered without breaking their order. The farthest galaxies, the web of clusters and voids, the ancient microwave glow, the long dark interval before stars, the first luminous objects, the unseen framework of dark matter, the accelerating expansion shaped by dark energy, the hot plasma, the brief making of light nuclei, the quark-gluon state, the breaking of early symmetries, the possible burst of inflation, and the uncertain Planck boundary all belong to one continuous answer. What existed before humans is not one thing, not one lost world, not one vanished civilization hidden beneath the surface of history. It is an immense succession of physical states, each more remote from human experience, each less concerned with life, and each more fundamental to the existence of everything that comes later. Humans arrive very late. Earth forms only after many billions of years of cosmic evolution. The sun forms from gas already enriched by earlier generations of stars. The atoms in rock, ocean, and bone are assembled through processes that begin long before the solar system exists. Hydrogen comes largely from the early universe. Helium also emerges there in abundance. Carbon, oxygen, iron, and many other heavier elements are forged later in stars and scattered by stellar death. The material basis of the human body is therefore a layered inheritance from earlier cosmic stages. Before humans, there is first a universe without biology, then a universe without planets, then a universe without stars, then a universe without atoms, then a universe without nuclei, and finally a regime where even familiar concepts of matter and time become uncertain. This sequence has a severe simplicity. The closer science moves toward the earlier stages, the less the universe resembles a place prepared for creatures. It is not a silent earth waiting in darkness. It is not a hidden garden, a buried continent, or a forgotten species. It is an expanding physical reality governed by temperature, density, radiation, quantum fields, and gravity. The answer unsettles because it removes the human frame so completely. Human history becomes a thin recent event near the surface of a much older and more impersonal order. Even biological evolution, immense on its own scale, occupies only a brief interval after planets, chemistry, and stable stars become possible. The deeper past belongs almost entirely to non-living physics. Observations support this layered picture with remarkable strength. The recession of galaxies shows expansion. The cosmic microwave background preserves the record of an early hot plasma, and the tiny fluctuations from which later structure grows. The abundance of hydrogen, helium, and deuterium supports primordial nucleosynthesis. The large-scale distribution of galaxies fits the growth of structure under gravity, with dark matter shaping the invisible framework. High-energy experiments support the existence of quark-gluon conditions and the particle physics needed for the early universe. The electroweak theory describes how particles acquire mass through the Higgs field. Inflation remains a leading explanation for the smoothness and near flatness of the cosmos, though it is not proved in final form. The Planck boundary marks the point where present theory becomes incomplete. Each layer is supported to a different degree, but together they form a coherent descent toward the earliest known conditions. What remains uncertain is equally important. Dark matter is strongly indicated by gravity, but its fundamental nature is still unknown. Dark energy describes the observed acceleration of expansion, but its physical origin remains unclear. Inflation is powerful and widely studied, but its exact mechanism is unsettled. The apparent singularity at the beginning of classical expansion may signal a true beginning, or it may signal the failure of current theory in that regime. Time itself may begin with the early universe, or it may emerge from something deeper, or it may continue through a prior phase not yet confirmed. Science does not fill these uncertainties with invention. It marks them, tests them, and leaves them open where evidence is not yet sufficient. So the deepest scientific answer is calm and unsentimental. Before humans, there is first the universe's structure, then the universe's radiation and plasma, then the universe's nuclei and particles, and then perhaps a domain where even these categories give way to something more fundamental. The terror sometimes attached to this answer does not come from monsters or sudden danger. It comes from scale, indifference, and the removal of familiar reference points. Humans are not standing near the beginning of things. They are living in a late and local after-effect of processes that begin long before any memory, or language exists. The cosmos does not begin with life and move outward. It begins, as far as evidence can trace it, with physical conditions so extreme and so impersonal that life is absent not as a special case, but as something not yet imaginable within the state of the universe itself. In that sense, what exists before humans is the long pre-human reality from which humans eventually emerge, expanding space, cooling radiation, gathering matter, burning stars, scattered elements, formed planets, and only then the slow arrival of living systems able to ask what came before. The question folds back into the answer. The beings who ask it are made from the outcome of the very history they seek to understand. Their bodies contain ancient hydrogen, recycled stellar carbon, and calcium forged in earlier stars. Their minds arise on a small planet orbiting a late-generation star in one galaxy, among hundreds of billions within the observable universe. They are not separate from the pre-human cosmos. They are one temporary expression of it. At the innermost limit, the most honest scientific answer remains unfinished. Observations indicate a deep past of extraordinary age and transformation. It remains uncertain whether that past has an absolute beginning in time, or whether a deeper layer precedes the earliest hot universe. Yet even with that uncertainty, the answer is already immense. Before humans, there is almost all of cosmic history. Before memory, there is physics. Before story, there is expansion. Before the first living cell, there is a universe that spends billions of years becoming capable of chemistry, planets, and thought. That is the great inward fact. Humans do not stand near the entrance of existence. They appear very late, inside a reality that is older, larger, quieter, and less human than almost any instinct is prepared to accept. The long descent now comes to rest in a quiet understanding. Before humans, there is no missing kingdom waiting just behind recorded history, no secret age of familiar beings, no hidden chamber of the world where human meaning already sleeps in place. There is a far deeper sequence. There is the earth before people, then the earth before life with bones, then the earth before life of any kind, then the sun before planets settle, then earlier stars making the heavy elements, then galaxies gathering in darkness, then the first stars, then only gas, radiation, and invisible mass, then the hot plasma of the young universe, then the first nuclei, then free quarks and fields, and then a boundary where present knowledge grows thin. In this slow view, the human world becomes very small, though not unimportant. It becomes local, it becomes recent. Thought, memory, language, and fear all arrive near the surface of a much older reality. The atoms that take part in thought are ancient. The light elements come from the early universe. Many heavier elements come from long-dead stars. The body is a late arrangement of very old matter. The mind is a later arrangement still. Science does not fill the deepest dark with legend. It keeps what can be measured, separates what is well supported from what remains uncertain, and leaves the earliest threshold open where evidence still falls silent. That restraint is part of the calm. The universe does not become smaller because some parts remain unknown. It becomes more precise. What is known is already vast enough. Before humans, there is almost everything. There is time beyond instinct, distance beyond memory, and change unfolding without witness. Out of that long impersonal history at last comes one small planet where matter learns to look back.